So today's lecture will be mostly about inverses. Okay, first we'll have a generic discussion about what inverse is. So you know what literal meaning of inverse is if you do something and you invert it. So in terms of say algebra, if you have a number 3, so you have to define some identity number. So identity number is suppose 1. So by default 1 means like you have an equivalent which from where you start counting. So if you have to sort of invert this number, so inverse in that will mean that you have to get this identity number. So you have to operate on something, and after that you will get this inverse. So inverse will by default come with an operation also. So whenever you read about mathematics, so whenever you see something is defined there, then you will be also given an operation corresponding to that. Suppose if I am telling you what is the inverse of 3, so you should ask me the question with respect to what operation. So if I tell you with respect to say, and I should also define identity element for that. So even before this, I should define this is called as identity element. And this identity element is also defined with respect to operation. So this operation is star and the operation is multiplication. So identity element for this is 1 if the operation defined is multiplication. If the operation defined is addition, okay, then the identity element is 0. So identity element there is 0. So with respect to operations, you will see that the identity element also change. So now if you ask a question, so you are given a number 3 and with respect to multiplication, what is the inverse of this? So you will say 1 by 3 because you know that if I have to multiply these two numbers and it should give me the identity element. So 3 into 1 by 3 is equal to 1. Similarly, in case of addition, so if you have asked that we have a number 4, so what is the inverse of 4? If they are giving you the operation with you, so they are telling you that with respect to operation plus, what should be the inverse of number 4? So you know that the identity element of this is 0. That's how it is defined. And then you will write 4 minus 4 and this is minus 4. 4 plus and minus 4 is equal to 0. And now this minus 4 is the inverse of 4, but with respect to what? 0. With respect to plus, and identity element over here, this is how it is defined. Now when I am talking about inverses, okay, in matrices, because we have been discussing about linear algebra. So you know that what a matrix defines. A matrix multiplication, if you see, a matrix is nothing but it is some encapsulating something like which is called as linear transformation. And you know how do we capture that transformation? Because we perform matrix multiplication, and you know that's called matrix multiplication, but you could have named it anything. So the operation that you have here is matrix multiplication. I can write mm. This is the operation that is defined. Now you know that what is the identity element. So identity element with respect to matrix multiplication, how can we define it? So identity element should sort of do nothing. So that's why we can call it I. That is the identity matrix that we have. Suppose in case of 2 cross 2, we have this 1 0 and 0 1. So if you take any vector, say x comma y, if you multiply this with this, you know that how to see at this, it will give you back this. So matrix multiplication is transformation. And now you know that this matrix multiplication is an operation. So this is the identity element then. So if you multiply this with any vector, it will give the vector back. So similarly, why is this called as identity element or this? Because you add 0 to any number, 0 plus 4, 0 plus 9, it will give the number back. Okay, in this case, why is it called identity? So if you multiply any number with 1, it will give that number back. Say 4 into 1 is still 4. So that's why the identity element is changed based on the operations you perform. So similarly, now if you see this matrix, so the operation we are performing is called as matrix multiplication, and the matrix you know it's actually a linear transformation. Okay, so what should be the identity element? So identity element there is an identity matrix, because if you multiply this identity matrix with the vector, so it should give this vector back. So we are now done with the identity element. Okay, we somehow understood that this is the identity element, but you know that what should be the inverse of this? It's not always the case that we will have this identity. So we'll have sometimes a matrix A. Suppose we have this A, B, C and D will be our matrix, and now we will be given at the end the vector xy. So we have seen the geometrical notion of this is that this vector will be taken somewhere else. So this over here, if you see, this was called as transformation of I cap, and this was transform vector of j cap. So matrix was seen like this. So these basis vectors are transformed somewhere, and then once you multiply, so whole of this was called as T of v. So you have a vector, suppose this vector was vector v. Okay, once you multiply this, you transform this vector v. So what was this equal to? This will be equal to T of I cap plus x of T j cap. That's why this matrix multiplication is very important. You have to understand the depths of matrix multiplication. Now what we'll see is that if there is a matrix, it is operated on some vector and it is giving me some resultant vector. So that means that there should be a way we should undo it. We should undo the effect of this. So if I have this matrix, suppose I have a matrix 1 3 4 5, suppose something of this sort, and I have a vector which is 1 5. So whenever I make a matrix, you should see this is doing some linear transformation. If I make a vector, that means some image should pop up with two numbers or the arrow. So this arrow is there. Suppose in 2D coordinate 1 5, how can we represent it? Suppose this is something of this sort. This is 1 5. Once I take this, so this is a matrix, this is a linear transformation. This matrix is a linear transformation. What will it do is it will be operated on this vector, and this vector will land at somewhere else. Okay, so how can we compute that? You know that you will take linear combination of 1 4 plus linear combination of this 3 5. So once you perform this, so you will get 16 and 29. So this will be the vector. So this is where this vector will land. So this 1 5 is basically transformed. So there is a transformation that was performed on this, and it was transformed to the 16 and 29. So what we now want is we want to undo this transformation. So we want to go from here to here. So initially we are going from here to here. So we want to go from here to here. The first thing that you should know is everything will not be invertible. Okay, that's why the concept invertibility comes into picture. Therefore, how can I define it mathematically now? So ax was transformed into b. Okay, so what I should do is I should operate on this b to get this x back. So what I'll do is I'll suppose have something, so which I'll apply on this. Say let's call that a dash. So if I perform this a dash onto this b, it should give me back this x. Okay, that's what I do over here. So if you see over here, so if I now compare these two things, so I have this ax is equal to b. Now this was initially, this x vector was taken to b vector. We had this x vector and it was taken to b vector, in which I gave you the example over here. This 1 5 was taken to 16 29. This is x was taken to b. We want to undo this. We want to undo this. B should be taken back to x. So I have to again bring up a matrix. That's why I said I'll bring a dash, this a dash, and once I perform this ab, it should bring back this x from it. So what I can call is now over here, this a dash and a, they are inverse of each other, and this a dash is generally written as a inverse like this, a inverse, and this is read like this. Okay, so what we can conclude from this is, so in case of matrix multiply, a is a transformation. Once operated on x, okay, it will perform b. So if you operate this a inverse onto this, so this will give me x back. Okay, if you remember this thing, so this is what an inverse is. Okay, and there are conditions to see if a matrix is invertible, if a transformation is invertible. That will come. The first thing is you should understand is this is how we define this matrix multiply. This is how we define an inverse. So now what you can see is, if you see this x, you can cancel it out. What you will get is, you will get a inverse of a is equal to I. Okay, or you can similarly also write like this is not quite easy to prove. You can see a inverse is also equal to I. This inverse, if you see, this can be left inverse and this can also be right inverse, and they are the same. Okay, so by definition, how have we defined the inverse now? If we have a matrix a is basically what? It's a linear transformation. So it was operated on a x vector. Now let's see if it can be operated on any vector. So now if we apply inverse onto this, we'll get an identity vector. So that as also explained in terms of algebra. So if you have 3, you have multiplication as an operation, then 1 by 3 is the inverse. So if I can write it like this, a multiplied by a inverse, that is equal to 1. Okay, this 1 is our identity. So this is the definition of inverse. So geometrically, what does inverse mean? Inverse mean whatever you did, whatever the transformation this a matrix did, so this a inverse will undoes that. So whatever it did, so this a inverse will undo that. So whatever this has done, it will bring those vectors back to where they originally were. Now the question is that which matrices will have inverse? Okay, I think we have a question. Yes, please. Okay, now the question that I was trying to address is like when we are finding these inverse, if you understood the gist of inverse is a transformation which undoes or which undoes the thing that was done by earlier transformation. So now the thing is, which matrices are invertible? Okay, I'll not answer this question directly. What I'll do is we'll take a detour, which actually, like I'll first give you some examples and I'll show you why are they not invertible. Then we'll come to the conclusion. Sort of we'll rediscover the fact that okay, this is the property this matrix had, and that is why this is not invertible. Okay, let me take an example. I'll take an example 1 and maybe 2, and let's take an example 4 and say 8. So this is my matrix. Okay, if you look at this matrix, okay, so what I can do is I can do one thing. I can say multiply some vector onto this. I can have some vector over here. Let's call that vector say 4 and minus 1. Okay, so if I multiply this matrix with this vector, so I chose this entry specially. So why what will this give? So if you see this, so this 4 times of this is 4 times 1 2 minus, okay, this is 1 multiplied by 4 8. So if you see this, So this will also become 4 and this will become 8. This will become minus 4 and 8. So in total it will give you 0, 0 vector. Okay, so now what you saw over here, it gave you 0, 0 vector. Now is there a possible way, because I took a vector and I shrinked it to 0, 0 vector. So you consider it like this. You had some 2D plane of this sort. You had a 2D plane like this. And you took some vector like this. And you transformed the space in such a way. So you had this matrix something of this sort. Say 1, 2 and 4, 8. Because of this, you will perform a transformation on the whole vector space. So once you perform this, it took this vector, the vector that you saw over here, suppose. So this vector was our, say, this vector, 4 minus 1 vector. So it took this vector, though it's not 4 minus 1. Let's consider this is some vector AB, and it took this and it squished it to 0. Now the question is, can you bring it back? Okay, can you bring this? Can you bring 0, 0? Can you perform anything on this 0, 0? Okay, and can you bring this 4 minus 1 back? The answer is no. Why? Because if you know that if I multiply, suppose any matrix, so I'll take any matrix A, B, C, D. Okay, if I multiply it with 0, 0, and it'll always get 0. Okay, this is like this, A multiplied by 0 vector. Okay, this always will give me 0. That means if there is a vector, this vector, suppose this is non-zero vector. If this vector on multiplication with some matrix, that is some transformation was applied onto this and it was taken to 0. Some 0 vector was given. So what can you conclude? Will you see that this matrix is invertible? You cannot say that. Clearly, there is no other matrix that you will find which will undo the effect. The effect that this matrix produced on this vector, you cannot bring this vector back. Is this point clear? Any questions on this point? This is very important to understand. The first question that was asked is, there can be some other vector which will not be taken to 0, and maybe with respect to this matrix, if we write some other vector over here, probably it will give a non-zero vector. But the answer to that is, suppose if any vector of this or any vector which is non-zero, say we have a vector which is non-zero and a matrix A multiplied by V takes it to 0, then there will be no way that you can get this V back from the 0. If it's even failing for one case, that means this matrix is not invertible. The second point was how to see now this is like why does it do it? Because I told you this is a very spatial thing. So if you see this, I wrote 1 and probably 2 and then 4 and 8. And you see over here, the columns of this were dependent. They were dependent. That is, they were not spanning the whole space, they were rather lying on the same line. Okay, that is one more test. If you see that columns are dependent, okay, or now if you see, suppose if you see rows are also dependent in it, that's why it's so special. If you see over there, if you multiply this thing by 2, the rows are also dependent on each other. Okay, if you see that rows are dependent, rows or columns are dependent, then you can clearly see that the matrix is not invertible. Okay, it's not invertible, and you saw the case. Why? Because it will probably take a vector to 0. As a consequence of this, what will happen is it will take some vector, say A, X, it will take it to 0, and X will not be equal to, this will not be equal to 0. That is why you cannot get this 0, you cannot get the 0, you cannot get X back from this 0, because it was initially not equal to 0. That's why you can see the repercussions of this. If this was the case, so because of this, you cannot get X back out of 0. And that is why Ax is equal to 0. If this is satisfied for any non-zero vector, that means the matrix is not invertible. This is one test. So this is one test. And this is also easier to look. If you find somewhere, if you see this, rows or columns were dependent on each other, then you can say this is also matrix is not invertible. So we have one test. This is one test. This is another test. One more test based on the same thing is, if you are performing elimination, you are performing some elimination, suppose. If elimination produces n pivots, if it produces n pivots, then only the thing is invertible. Otherwise, it is not invertible. Okay, there exists inverse if and only if. So inverse will exist if and only if. So what is the case? The case is that there should be n pivots, and you know what a pivot is. So if you have, suppose 3 cross 3 matrix A, B, C, D, E, F, G, H, I. If you allow row exchange 7. If you allow row exchange are allowed. So what will happen? This is the first pivot element that you have. This is the second pivot element that you have in there. And similarly, this is the third pivot element that you have. So now what I'm saying is, if you have an n cross n element vector, so you have n cross n matrix. So you will say that inverse will only exist, okay, if these n pivots are there. So elimination should not reduce some of this pivot. So any of the pivots should not be 0. If any other pivot is 0 while you are eliminating the process, then you can clearly see The problem with this is that it is not invertible, and you can again go to this. Why will this happen? Probably the rows will be dependent. You will have these dependent rows that as a consequence of that, probably something will become 0. And you might have heard that in the elimination process, while you are finding the inverse, because you generally people find inverse by using elimination process. They'll say that if two rows become same, that is they become independent. Okay, if they become dependent, sorry, so the inverse doesn't exist. That's what I'm saying over here. So if row extensions are allowed, and inverse will only exist, and inverse will exist if and only if there are n pivots. So if even a single pivot is gone, that means at least one row was dependent, like over some other rows. That means the inverse won't exist. So it is all the consequence of whatever I said it over here, and there are different ways of saying it. You might have heard it in different terms, but if you see this, you might have also heard. Okay, this you might have also heard. But if you see the matrix multiplication and you understood it, and then you will be easily able to see how important this was. I think we have a question. Yes, please. Now, if you understood this about inverse, and there are different properties of inverses. Okay, suppose if you have this inverse, so you have A, B is equal to I. That means A and B are inverses together. Suppose if you have now A and suppose C, that's also equal to I. So you can easily prove that this B is equal to C, something of this sort. So let's suppose this A was over here, B was inverse of A, C was also inverse of A. You can easily prove that B is equal to C. That means if inverse, it is unique. If inverse exists, it is unique. Okay, I can leave the proof to you people. So how you can prove? It's a two-liner proof. You can easily prove it. That's why I'm leaving these proofs to you people. But whatever you, so howsoever you decide to prove, you will find that if there is an inverse, if inverse exists, it's always unique. Okay, so these are different ways. So what we did so far is we defined what an inverse is. Okay, and we defined it in the generic sense. And the second thing is then we saw what are the different ways to check if the inverse is there, if inverse exists. There are more ways. You might have heard about determinant. There is a way of determinant also. If the determinant of suppose a matrix A is non-zero, then only inverse exists. Okay, we'll also go there once we read about determinants. But this is also one of the ways to check it. Now let's see how to find the inverse. The question is now how to find the inverse. If you are given a transformation, then how can you find the inverse? The first we'll go to bare bone basics, and we will not use the adjoint method, this and that method. We'll see what can we do. So we have this. So we have something of this sort. We have A, X is taking it to B. So this was the initial equation that we had. So I was given say some matrix A, and then I was given a vector X, and this X vector was taken by this matrix to B. Okay, this linear transform was done. So now I have to undo this. I have to undo whatever. Basically, what I have to do is I have to find A inverse is I. This is what I want. So this should be whatever the operation would be performed. So it should take it back. So how to perform this? So if you see this, if I have a matrix suppose of this sort, A, B, C, and D. Okay, now what you have is you have this. Suppose some matrix, say I can write it X, Y, P, Q, something of this sort. Say this is my matrix. So this is my matrix. Okay, and this matrix, if I call it an inverse matrix. So this is suppose A inverse, and this is my A. I know this is equal to identity. This will be equal to 1, 0, 0, and 1. Okay, everybody agrees on this because we have established this from the definition. So what I'm saying is, suppose this is my matrix now, or this is my first transformation, and this transformation is that transformation which undoes this. So effectively what I should get this I. So now if you again see it, if you look carefully in this, so can't I do this? Can I do something of this sort, A, C, or A, B, D, something of this, and then I'll take this XP, the first vector. Can't I write this equal to 1, 0? Because you know that this column is the linear combination of columns of this. So how did we get this column? Because we took this column and multiplied with the whole vector, and then we got this column. So under the assumption there, you understood how do we perform multiplication. So this is pretty valid. And second thing is I can write also this. I can write A, B, C, and D, and then suppose this Y and Z, or Y and Q, sorry, Y and Q, the thing over here, Y and Q. This is also equal to 0, 1. Okay, now you can clearly see over here, these are now sort of linear equations. So these are linear equations. The equations that we earlier had, we had suppose 3x plus 4y minus 2z is equal to 1, something of this sort. Then we had some other equations, and then we were taking coefficients out. Okay, then we are taking this x, y, z, and then we are writing these equations, and we are converting them into this matrix notation. So how do we solve those linear equations? If you had linear equations 4x plus y minus 2 is equal to 0, minus 2z, and then we had 3x plus 2y plus 6z is equal to 9. So you see we had these linear equations, and then it had 3 variables, and we are given this. So we'll take coefficients out. So you know what we'll do is we'll take this 3, 4, 3. Then we'll take 4, 1 and 2, then we'll take -2, -2 and 6. And then in order to solve this, we were using elimination, which we called as Gauss elimination process, Gauss elimination. If you see the same process over here, if you understood this, how can we can make some lower triangular matrix, and you know what to do. We'll use this as pivot, and we have coded that up, and we'll make these entries 0, and then you'll take the second pivot, and then you'll make this entry as 0, and you'll keep on going, depends on the size of the matrix. So now you saw this problem is exactly similar. So this thing will give you equation, it will give you linear equations. So what we can do is we can again apply this Gauss elimination. Okay, so what Gauss thought is, okay, they said, okay, this is a very easy problem to do. What we can do is we can take this A, B, C, D. So let's suppose we have this. So initially we had, say, A, B, C, D. This is what we have to find. Okay, and we have suppose X, Y, P, and Q. This was the inverse that we had to find, and this was our identity. And this was 1, 0, 0, 1. So what I can do is, if I can do something of this sort, if I can take X, Y, P, and Q, and I can eliminate this, I can equate these things, and I can for back substitute, and then I can make this as a lower triangular matrix, and then I can back substitute the values. I can find these values. So but the one thing that we should do is we should sort of stuck these variables, this 1, 0, and 0, 1. Okay, so what should happen is I should make this as identity now. This should be turned into identity, and whatever happens, this will become A inverse. Okay, this is what Jordan said. Okay, that's why this method is called as Gauss-Jordan method, because we were doing Gaussian elimination. Gaussian elimination was to eliminate this, but what Jordan said is do one more step. So you have to augment this. You take this matrix and whatever operations you are doing on this, okay, make it an identity matrix somehow. Okay, you should make it this identity matrix, and then what will happen to this will give you the inverse. Okay, that's what we did over here. So if you have, suppose some matrix was there, we had this A, okay, and then we took this I. So once you perform this, so this will become, suppose if we make this as identity, and this will be turned into B. Okay, this once we keep on performing calculations, because you know that here this will automatically, because we were in a process that we were equating it to 1, 0. So what will happen is, so this B over here, so if this is converted into identity, so this B over here will become A inverse. So why will this become, if you equate these things, so you will get A, B is equal to identity. That's why this B is the inverse of A. So if you have this AI and you covered it, you did this, you performed an inverse operation on this, and then you made sure that this becomes I, and you can see that this will become A inverse. So if you equate these things, because you are keep on doing these operations, so you will see that automatically, if I had a matrix of this sort, you had initially A, and you augment I matrix on this, and then you apply Gauss-Jordan method on this, and you know what Gauss-Jordan is, you have to perform basically Gaussian elimination. Okay, and then Jordan said also have this A with you. So this you will get this B, and then you will get this I, and then you will get some other matrix B, and this we will call as A inverse, and this will be the inverse of that. Any questions still here? Okay, we will perform Gauss-Jordan operation on this. So what I would have is, so suppose we have a matrix 2, -1, 0, -1, 2, -1, 0, -1, and 2. Okay, this, and we have to find inverse of this. Now that you know that if I augment this identity matrix onto it, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So if we have, if this was not there, suppose, so what we have done is we would do, suppose, Gaussian elimination to solve this, because as I told you over here, this was the case. So this is almost equivalent. So solving this is equivalent, because we have to find this A, B, C, and D. That's how that is finding the inverse basically. So solving this is equal to, if we take this equation, suppose, okay, if we take these will be some constant numbers given to us, suppose 1, 2, 3, 4, and these will be the coefficients that we have. Okay, this is coefficients, and these are, suppose, variables, and then these are the this is 1, 0, and 0. These will be equations. That's what Jordan said. Okay, don't stop, don't just perform Gaussian elimination. Convert this whole thing into I. Okay, and you will see that this will get into A inverse, because you are converting this into A, and you are something doing like this. So you had an A, you are doing A inverse. Okay, and that is giving you I over here. So what will happen to this I then? So I also got multiplied by A inverse, because that is what you did over here. So you had something over here, and you multiplied it with A inverse, and it was transformed into I. That means you are also multiplying I with A inverse. That means this I will get transformed into A inverse. Okay, that's what I also explained previously. So now what Gauss-Jordan will do is, they will do the same thing. So they will take the first pivot and make the other things as 0. Okay, let's suppose the first operation they will perform is 1 by 2 of row 1 plus row 2. Okay, because this will be the pivot element. Okay, and then this entry will be made 0, and this is by default 0. So if you see the consequence of this, you will get, suppose 2, 0, 0, -1, 3 by 2, -1, 0, -1, and 2. But the matrix is augmented onto this. You can write 1, 0, 0, and second row was operated. So you'll see 1 by 2, 1, 0, 0, 0, 1. This is what happened to this. So on performing this operation, and this was done to R2. So R2 was done 1 by 2, R1 plus R2. This is the first operation that we performed. Similarly, again, now the pivot becomes this. Okay, what will Gauss do? Gauss will say, okay, you have to make this entry 0. So you'll say 2 by 3 of row 2 plus row 3. Okay, put this into row 3. Okay, what will be the consequence of this? So it will become 2 minus 1, 0, 0, 3 by 2 minus 1, 0, 0, 4 by 3. And the augmentation will similarly will have keep also track of whatever operations we performed here. We should also perform those here. So 1, 0, 0, 1 by 2, 1, 0, and this is 1 by 3, 2 by 3, and 1. Now we are stopping here. In the Gaussian method, once we perform Gaussian elimination, we'll stop here because we got this lower triangular. If you see, we got this upper triangular matrix. So we got these zeros over here, non-diagonal elements by 0. Now what Jordan said is, okay, don't stop here. What you have to do is, you also make the above elements of the pivot 0. Suppose now this is the pivot, you also make this 0. This is the pivot, you also make these 0. Okay, you don't stop over here, you perform the Gaussian elimination in the backward way. So initially you are doing Gaussian elimination in the forward way. You don't stop over here, you perform this elimination in the backward way also, because we have to get zeros everywhere. Why? Because we want to knock out every variable, because we want to make I out of this. So what will happen because of this? So the operations that we perform is 3 by 4 of row 3 plus row 2. Okay, and this will be given to suppose row 2, because we have to make sure that these entries are 0. This entry is 0. Okay, and after that we'll make sure that this entry and this entry is 0. So after this we'll make one more operation, that is 2 by 3 of row 2 plus row 1. This is how we'll change row 1 also. Okay, we want to eliminate this entry and then we want to eliminate this entry. This is done to row 2 and this is done to row 1. So after elimination, so what you will get is, you will get 2, 0, 0, and this is 0, 3 by 2, 0, 0, 0, and 4 by 3. I'm just showing you the mechanical process, and calculations can be here and there. Don't worry about those. 1 by 2, 3 by 4, 3 by 2, because nowhere in our life we will be doing this with this in hand. We'll be majority of the times doing it with computers. So now what you have is, you made all these non-pivot entries as 0. So you have to make these things as 1. So what you can do is, you can just divide these things by, you can divide the first row by 2, divide this by 3 by 2, divide this by 4 by 3, and you will get 1, and then accordingly the same operations will be done over here. So that is why this is called Gauss-Jordan method. So if you do that, if you now do that, so what you will get is this. So this will become identity. Once you divide this by 2, divide this by 3 by 2, divide this by 4 by 2, what will happen is, you will get 1, 0, and 0, 0, 1, 0, 0, 0, and 1. So this is how this was transformed. And this will be transformed like this. This over here will be transformed by 3 by 4, 1 by 2, 1 by 4, 1 by 2, 1, 1 by 2, 1 by 4, 1 by 2, and 3 by 4. And this over here is the inverse. Why? Again, I am telling you, suppose we have a matrix A, so you transform this into I. So what happened to this? Maybe you multiplied it with A inverse. And in parallel you had I, and you performed the same operation, that is this A inverse was also applied then, that is A inverse. So this will also be transformed into A inverse. Then if this was transformed to I, automatically this will be transformed to A inverse. So what we did in Gauss-Jordan method, whatever Gaussian elimination we did, but we did it forward and backward as well as, because we want all the non-pivot entries as 0. Okay, that's what we did, and we performed the same operation onto this as well. And then diagonal elements had to make 1, so we divided those diagonal elements accordingly, and we also divided those, and you got this inverse over here. Any questions on finding the inverse? So what we saw over here is, if we have to now compute the cost of elimination. Cost of elimination. So we saw that Gauss-Jordan method. If I go back to the topics, like I'll show you the map that we are following. The first thing that we discussed is, what is an inverse. So we defined an inverse for us. Okay. After that we said ways to check if inverse exists, and there are different ways we check. And the third topic that we were finding is, find the inverse, and there is a solution for this, and we call that method the Gauss-Jordan method. Gauss-Jordan method, and Gauss-Jordan method was nothing but just an extension of Gaussian elimination. So basically we are doing elimination on that. So now I want to see what is the cost of elimination if we perform it in computer. So what is the cost then? So what I said is, let's suppose we'll take an n cross n matrix on which we are performing elimination. So this is our n cross n matrix. So we have n elements over here, and we have n elements row wise and column wise. That is, we have in total n square elements. So you'll select the first pivot. You'll select the first pivot element, and whatever is below this, you'll make it 0. Okay, basically what we are doing is, if I take say addition and multiplication, because you will multiply the whole row with some factor first, and then you will add or subtract it. So add, subtract, or multiplication, division, this will be considered as one operation. Suppose let's say this is one operation. That means once we perform the first, using the first pivot, once you do the first step of elimination, so it will perform n square operations, because it will operate almost on all the elements that we have over here. Now after that we'll have second pivot. So second pivot will leave us to operate on this sort of matrix, that is n minus 1 matrix. So we will have plus n minus 1 whole square operations will be performed. Similarly, then we'll select third pivot, and third pivot will give us n minus 3 plus n minus 3 whole square, and so on, plus 3 plus 2 plus 1. So what is this sum equal to? If you just use your brain and do the sanity check, what you will do is you say I have this n square term, and this is n times, sort of, if I sort of say this is n times, this is almost equal to n is like n square times this, that's n cube. You can roughly say it's order n cube. If you have to find exact answer, what you can see is you can see this sum is almost equal to integral of 0 to n, suppose x square. Okay, this is what it is. So if you expand this in summation terms, so what you will get is you will get exactly this sum if you use calculus. So you know what is the integration of this? This is x cube or n cube by 3, or this is 1 by 3, this is 1 by 3 n cube. So what I'm saying is now you'll also do forward elimination, backward elimination, you'll also count in those factors, and you can also apply it on identity, but still you will get the answer in order of n cube. This is the computational complexity, or the time that will be required to perform these operations. Yes, questions? So this is what we did. So far what we have done is we have answered a couple of questions, what an inverse is, like how to decide if a matrix is invertible, and then we also saw properties of inverse and other stuff, and then we saw how to find the inverse. So that there we saw Gauss-Jordan method, and then we also performed a computational complexity cost. So what is the cost of performing this Gauss-Jordan operations? Properties of inverses. Suppose you have this a and b now. If you have to find inverse of this, so how, so what is inverse of this? If you have suppose b inverse and you have this, you have a inverse for a and you have b inverse for b. So if you have to invert this, so you know that matrix multiplication is associative. What you will do is you will take b inverse and then a inverse. Okay, and this, if this whole AB is the matrix, and then this is the inverse of that. So you have AB, and AB inverse is basically equal to, this is equal to B inverse A inverse, and you know why? Why? Because we perform matrix multiplication is associative. So what you can do, you can say AB, B inverse, A inverse. You can associate these two first. This will be identity, and then you can associate these two things, and then this becomes the identity. So that means AB inverse is basically equal to B inverse, A inverse. This is equal to identity. That's what I wanted to show over here, because we have to use this. Now we'll go to a very interesting topic, okay, that is called as factorization or decomposition of matrices. Factorization or decomposition. Of matrices. So what is this topic? This is related to inverses. Okay. So as we were solving the fundamental problem of calculus, in which we were solving linear equations, we had a set of linear equations, and in which we had set of variables. So the equation that we had taken in the previous class, we had three equations: 2x plus 4y minus 2z is equal to. The second equation was 4x plus 9y minus 3z is equal to 8, and then this was minus 2x minus 3y plus 7z, that is equal to 10. So these are the set of equations, and we know that in order to solve this, so if I take options out, I can form ax is equal to b equation out of this, and then after reducing the equation, we can apply elimination on this. We were getting some upper triangular matrix, and this x is equal to some c, and this upper triangular matrix was easy to solve, and then we were using this upper triangular and back substituting. So we are using back substitution in order to get the solution of this. Now, if you understood this, if you understood how we perform this UX is how we perform the elimination method basically. So what we can do is we can see it in a different light. So these were the three equations, and we had three variables. So what I said is, if I take options out of this, so you'll have ax is equal to b, and after applying the elimination method that we studied, we take a pivot and then we make the below entry 0. You are getting this matrix ux is equal to c. So this ux is the upper triangular matrix, and you know why do we get upper triangular matrix? Because we knock out some variables and then we can easily back substitute. So what I'm telling you is, now we'll look at the same concept in a different light. So the first step that we did, so we had this matrix. So if we take this a is equal to, I'm taking coefficients out, 2, 4, minus 2, this is 4, 9 and minus 3, and this is minus 2, 3 and 7. And then you know x is equal to x, y and z. And then we had this b is equal to 2, 8 and 10, 2, 8, 10. So I'm just making matrices out of these things. So whatever we had, these equations are out here. So I'm taking these coefficients out, taking the x, y, and z out, and taking this 2, 8, and 10 out. That's step 1 in the elimination. If you see that we had this 2 times r1. So you multiplied the R1 row, the first row of the matrix. So this matrix you multiply it with 2 because you wanted to knock out this 4, and then you subtracted this from R2. So row number second was subtracted from by 2 R1, and you change this R2 somehow. So if you see this, so just keep this at the back of the head. So I'll just put a dot over here. So we'll come back here. So now if I first show you the matrix multiplication, suppose I'm given a matrix, I'm given 1, 3, 5, something of this sort, 1, 3, 5, 6, 2, 9, 8, 1, 2, something of this sort. So if I'm asked to multiply it by a column, my column will be 2, 3, 4. So this is my matrix. So this is my matrix, and this is a column vector. So if I'm asked to multiply it, you know the usual way of multiplication is we'll take suppose this and then we'll multiply it with this and we'll get entry. So this is 3 cross 3 and this is 3 cross 1. The resultant vector that we will have will be of size or dimensions 3 cross 1. So now the question over here is how do we do it in traditional way? So you'll take whole of this and you will multiply it with this, you'll get this entry. And then you will take and the row, you'll multiply with the whole of this vector and you'll get second entry. So for you'll take third row and again this vector, you'll get the third entry. But I'll show you a different way of looking at it. So you can focus over here for a second or so that you get the gist of what I'm trying to convey. So how you can write this? So you can see, you can take 2 of this and multiply it with the whole column of this. So you can say 2 multiplied by 1, 3 and 5 plus 3 multiplied by, so this 3 and multiplied by 6, 2 and 9 plus 4 multiplied by 8, 1 and 2. So if you now do this calculation, it is equivalent to the method that you have been taught in the schools. You have been taught that you take this row and multiply it with this column, you'll get the first entry, take the second row, multiply again with the column, you'll get second entry, and for the third entry, you take the third row and multiply it with the column, you'll get the third entry. But what I'm saying is, I'm saying that in order to see this in the different way, so you can take this column, each entry of this column can be multiplied with this. So you're multiplying this 2 with the first column, you're multiplying 3 with the second column, you're multiplying 4 with the third column. Now, isn't it the way we are taking linear combination of columns? So this is linear combination of columns, and you are getting a column here, you are getting one column here. So columns in the resultant matrix, so you can remember this thing, columns in the resultant matrix or in the resultant is the linear combination or the linear combination of columns of, suppose this A matrix, columns of matrix A. You understood what I'm trying to convey. You can write it in better English than mine. So what I'm saying is that in order to find this matrix, so here you had the resultant as just one column. So this column actually was linear combination of columns of this. So I was taking 2 of this column, I was taking 3 of this column, and I was taking 4 of this column in order to get this column. So if you have a matrix and you want to multiply it with a column, so you'll get a column. So how you can see is, you can see that columns of this resultant matrix is linear combination of columns of this A matrix, the first matrix. Okay. I hope that you agree on this point and you're clear with this. The second point I want to show is, suppose you again have a matrix. You have the 1, 2, 3, 8, 9, 6, 1, 4, 9. You have something of this sort. Now, if you are given a row from this side, you are given a row 1, 4, 3, something of this sort. Now you know that the dimensions of this is 1 cross 3. Dimension of this is 3 cross 3. The resultant will be 1 cross 3. 1 cross 3. Pretty obvious over here because I gave you the hint earlier. So if we are speaking about resultants of resultant matrices column, so columns of resultant matrix, we are saying that columns of this resultant matrix are the linear combination of columns of the matrix on the left hand side. Now in this case, if you are taking the rows at a time, so now what you can do is, in order to form this row, you can take this and multiply it with row of 1. You can take this and multiply it with row 2. You can take the third entry, multiply with this. So basically rows of resultant or the linear combinations of the other matrix that's on the right hand side. Suppose we'll call this matrix say X. So now if you call this matrix as R, so rows of R are the linear combination of rows of this X matrix. How? So I can write 1 multiplied by row 1 plus 4 multiplied by row 2. Now you know R1 is whole of this, R2 is whole of this, and R3 is whole of this, plus 3 multiplied by R3. So you will get a row of this resultant vector. So I showed you 2 ways. So initially what I did is, I had a matrix and I had a column. So now once I was multiplying them, I was getting a column as a resultant. So I can see that column as a linear combination of columns of the matrix on the left hand side. So you had this matrix on the left hand side. So column of this resultant vector by the linear combination of columns of this matrix, matrix A. Now I have a matrix which is on the right hand side and I can see it. I can see the rows. I can see a row vector which is multiplied by, which we can multiply to this. So now after getting the resultant, I can clearly see that the rows of this, the rows of resultant vector, the linear combination of rows of the right matrix. So you people should be clear on these 2 points, because I told you to hold on a point, that is this should be at the back of your head. How many of you are clear on to these 2 points? The first and two. I showed you 2 ways to look at the multiplication. One is the linear combination of rows, and one is the linear combination of columns. So how many of you are clear on these 2 points? If you are clear, then we can move forward. If all of you people agree on this, that these 2 are the things that you sort of find justified and there is no illegality or mathematical problems in this, then we can move forward. Now the question that I had we were doing these operations. So if you see how are we eliminating the variables, we're using some rules that we wrote in the previous lecture. So the first step that we performed on the matrix was 2 times of R1, you multiplied the first row of the matrix by 2, and then you subtracted R2 with this, and then you are knocking off one variable. You want to knock off this variable. So basically how I can write it, so you had a matrix like this. You had a matrix 2, 4, minus 2, 4, 9, minus 3, minus 2, minus 3, and 7. Okay, somehow you wanted to do this. So what you wanted to do is, because you had to perform this move, 2 times of R1, and you should be subtracting this from R2, and this is how you can substitute this with R2. So what I can say, I don't have to do anything with row 1. Okay, I don't have to touch it. So I have to get some resultant where I don't touch this R1. So I am keeping R1 as it is. Okay, I don't have to touch this row. Okay, but somehow I have to make change in this row. I have to subtract from this row. So this row should be taken 1 of this row, and it should be subtracted with 2 of this row. So what should I multiply over here? So if you see, I have to multiply something. Something should be multiplied over here so as to get this. I'll show you a different way of looking at it. So for the first row, I have to keep it unchanged. If I have to keep it unchanged, because I told you, if I have a matrix on left hand side, if I have a row at left hand side, so the row of this is a linear combination of rows of this. So in order to keep this row as it is, so I'll keep 1 over here and then 0 and 0. So now you take linear combination of this. This is 1 of this, 0 of this, and 0 of this. So you land here. So you'll get the first row as it is. So what I'm doing is 1, 0, 0. Similarly for the third row, I have to keep it same as it was. So how can you do that? So I'll say 0, 0, 1. I'm taking 0 of this, 0 of this, and 1 of this, because I know that this basically row 3 is the linear combination of these 3 rows, and pretty easy because I have to keep this row as same. So I'm keeping 0 of this, 0 of this, and 1 of this. That's what I'm writing. Suppose I don't have to change the matrix at all. If I have to keep this matrix as is. So what I will do is I'll say 0, 1, and 0, and you know this is called identity matrix. Why is it called identity matrix? Because if I multiply this matrix with this, you will get the matrix back. You will get this matrix back. So I'm taking 1 of this, 0 of this, 0 of this for the first row. For the second row, I'm taking 0 of this, 1 of this, and 0 of this. I'll get the second row. So in the third row, I'm taking 0 of this, 0 of this, and 1 of this. I'll get this row. But if you see this move now, see it carefully. So I am not allowed to do this because I don't have to keep it the same. I have to somehow change it. So how can I change it? I have to multiply the first row with 2 times. Okay, so I have to multiply this 2 times. So how I can do that? I have to write 2 over there, but I just don't have to multiply it only. This is like minus 2 because I'm adding it also. So what I'll do is I'll say minus 2. Okay, and then this will be minus 2 of this row, and then add 1 of this row because it's a linear combination. So I'll take 1 of this row and none of this row. I'll say 0 of this row. So how many of you are convinced that this matrix is performing this step? The step I wrote over here. So this is the matrix that is performing that step. If you people agree on this, then we can move forward. If you have some argument against it, do tell me. Just look at the matrix. So now that you saw it, what I did is I changed these steps into matrix notation. I was performing some elementary transformations. These are called elementary transformations. These are called elementary transformations. I was performing something on rows and then doing something, and this can be represented in matrix. This is the matrix notation of that, and these matrices are then called as elementary matrices. Okay, so these are called elementary matrices. I am performing some elementary operations, and whatever I am getting, I am calling them as elementary matrices. So now what I can write is I can write this matrix as E1, suppose. So this is my E1. So I can say E1 multiplied by A. So I multiplied it with A. So what I got is, so I got this matrix because I knocked out one variable. I got 2, 4, minus 2, 0, 1, and 1, minus 2, minus 3, and 7. Because I kept these 2 rows as similar. I kept the first row and the second row as similar. I performed on the first and the third row. I performed operations in the second row, and I had to knock out this variable, which I did. So this is what I did. So similarly, I'll have to perform also E1 multiplied by B, because B also has to be transformed as it also has an impact over, because when this is multiplied with this matrix, automatically B will get changed. So when you perform this E1, when you multiply that with B, and you know how to perform that, it's a linear combination of rows of this E1 matrix. So take rows of this and perform this multiplication of B, and you know what B is. So B is over here. So B is 2, 8, 10. So you take 2 of the first column of this E1 matrix, 2 of this, so 8 of this and 10 of this. So what will you get? You'll get 2, 4, 10. E1B, this is 2, 4 and 10. So this is the first step. When you perform the first elementary transformation, so I wrote that into matrix notation, and that matrix was E1. So after that, I again operated on this matrix. Now I had this matrix as a matrix. I want to knock out this variable. So what I did is, if you see the second row, we just added that. We said R3 is the value of this is R3 plus R1. This was the elementary transformation that was done. So you have to add this and this so as to get 0 over here, because we are knocking out the variables. We are knocking out the entries that are below this pivot, because first pivot is this. So now again, this can be written in the elementary transformation. How can you do that? Similarly, you write this matrix. I'll again show this matrix. This is 2, 4 and minus 2. This is 0, 1 and 1, and then we have minus 2, minus 3 and 7. Minus 3 and 7. Now you have to keep the first entry same. You don't have to touch it. So if we don't have to touch it, so we'll say 1 of this, 0 of this, 0 of this. So it will be 1, 0 and 0. But second entry also have to be kept as it is. Second row is to be kept as it is. So what we can do is, so we can say 0 of the first row and the 1 of this row and none of this row. So linear combination means this, because I don't have to touch these two rows. I have to somehow touch this row. So what can I do is, so I have to take one of the initial row and let's say one of the last row and none of the bottom row. So what can we do is, we can write E2. So E2 will be equal to 1 of the first row and then 0 of this and 1 of this row. So you're adding these two things. So this elementary transformation can be written in matrix notation like this. Okay, so what we have now is, so we initially had A matrix, the coefficient matrix. You multiply it with E1 and then you multiply it with E2. E2 is this matrix over here. Okay, and you will get some resultant matrix. So after performing that multiplication, because you know that the entries below the pivot will become 0 now, so you'll have 2, 0 and 0, and now you will have 4, 1 and 1. This is minus 2, 1 and 5. Okay, and these are two operations so far. Again, you have to do the same thing with B. So B multiplied E1 and E2. Okay, this is equal to 2, 4 and 12. You're constantly changing these as well. So now what you have to do is, you'll take this as pivot. Okay, and then you will knock out this entry. So what is that? So that, if you see that elementary operation, that was R3 minus R2. You take this R3. Okay, this is the R3 and you subtracted this R2 from it, because you want to make this entry as 0. So 1 minus 1 is 0. So you're doing that. And you can again form the elementary transformation. So what is the elementary matrix over here? E3 can be easily written. Because what we want to do is, you want to leave the first entry as is. You want to leave the third entry as is. But you want to make sure that this is turns out to be 0. This third entry is also 0. Second entry is left as is. So E3 will be equal to 1, 0, 0. 1 of the first row, none of second and third row. So because you are leaving it unchanged. You are leaving, suppose, second row also unchanged. So that's why you are writing 0, 1, 0. But for the third entry, what you are doing is, you are adding these two things. You are adding R2 and R3. And you are replacing it with R2. So what you can do is 0, minus 1 and 1. Subtract, rather not adding, subtracting. That's why I wrote minus 1 over here. So now what you can do is, you will get upper triangular matrix. You will get 0 entry over here as well. So now you have upper triangular matrix. So how I can write in matrix notation? You can write E1 multiplied by E2 multiplied by E3, and you multiplied this with A. Okay, similarly B got changed. So you had E1, E2, E3. You also multiplied this with B. So once you perform these multiplications, you will get a lower triangular matrix. So on this you will get, say, 2, 4 and minus 2. 0, 1 and 1, 0, 0 and 4. So you have converted this into lower triangular matrix. Similarly, in this case, you got 2, 4 and 8. And this is what you do with the elimination, but we did it in different notation. So initially you were doing it by using elementary transformations. So now what you did is, you change these elementary transformations into matrices. They are called elementary matrices, and you saw it like this. Okay. So now you know that matrix multiplication is associative. So if I have A, B and C matrix, that we will see again. But take a leap of faith over here. So this, if I multiply BC first, this will be equal to multiplying AB first and then C. So this is equivalent in matrix notation. So matrix multiplication is associative. So I could have multiplied E1 then A, then E2 and then multiplied with this. I could have put bracket over here. I could have done this, then this, then this. Okay. So or conversely, I could have first multiplied these three things and then performed this A. So what I am getting over here, if you see, this is my upper triangular matrix. I am getting this. So I am multiplying E1, E2 and I am multiplying E3. by A. So I'm getting some upper triangular matrix, some U. So if you see, I'm getting some upper triangular matrix over here when I'm performing this, because I want these zeros at the bottom and I have non-zero entries in the upper diagonal after the major diagonal. So you have this matrix. So somehow if I can replace all of these three matrices combinedly, so I can call that L, suppose. So I can call that, say, or maybe if I let's call that X for now, and then we'll bring that L. So you have this X now over here. So I can say X, which is equal to E1 multiplied by E2 multiplied by E3 in this order. So if I multiply this capital X, so I write this X a little bit fancy, so it's not confused with that AX. So this X is like this. So this X multiplied by A is equal to U. You are getting upper triangular matrix over here, because we combine this E1, E2 and E3. So now you see we got upper triangular matrix as a consequence of this. So if you directly multiply this, you will get upper triangular matrix. As a consequence of that, you can back substitute it. Once you back substitute it, what will happen is you will directly get the values for basically the final solution. The final solution will be X is equal, suppose, -1, Y is equal to 2, and Z is equal to 2. You can also get this. So now coming back to the original question, if you have this A matrix, you had E1, you had E2, and you had E3. These were your elementary sort of matrices that we got because of elementary row operation once we performed the Gaussian elimination, and you got this upper triangular matrix. So let's do one thing. So we'll do this. Say we have 1, 2, and 3, and let's say 4. Now if you have to perform elimination, you know that this will be the first pivot, and you will have to operate on this, and you will have to make this 0. So what can we do in this case is this. You will say I will multiply R1 with 3 times R1, and then minus of R2. Okay, and this will be given to R2. This is the operation that we have. That means you will take 1, 2, you'll do nothing to this. So but what will you do this? So this will be multiplied by 3, so that this will become 3 and this will become 6, and then suppose this will be subtracted. So you'll get 0 over here. 3 minus 3 is 0, and then you'll say 4 minus whatever. 4 minus, say this is your 6. 4 minus 6 is 2. Or we can do by reverse of this. We are taking out of this. So this is 3 and this is 6, and then you are subtracting this from this. 3 minus 3 is 0, and then 4 minus 6, this is 2. So you are getting something of this sort. So what I can do is I can write this in the elementary matrix notation. So how to do that? So suppose you have this. You have 1, 3, and this was 2, 4. So how can you perform elementary operation? First row you have to leave as it is. Okay. So you know that how to see matrix multiplicity, you already know it. I'll say I'll take 1 of this and 0 of this. So 1, 0, I have to nothing do. I have to do no change in the first row. But the second row, what I'll do is I'll take 3 times of this, 3 times of first row, and then minus 1 times of second row. This is what this elementary matrix over here, this basically represents this. If you see this over here, or we can do it in the reverse order also. You can say minus 3, 1, something of this sort. If you do it like this, R2 minus 3 times R1, okay, then this operation will be over here. So what will this give me? So if I say do it like this, so I am taking R2 is 3, 4, and I am subtracting thrice of this. This is 3 and this is 6, and you will get minus 2 over here then, if I just reverse the operation order. So I am getting this. So this over here is my E1. So elementary matrix 1, which I got because of this, because I am taking 1 of this and none of this. Okay, I am not changing the first row. That's why I am taking 1 of this. If you see this row, I am taking minus 3 times of this and then adding it with this. Okay, if you see this E1, so and to figure out this, so you got now E1 and A. This will be some matrix, let's suppose X dash, something of this sort. Now to sort of inverse, to find inverse of this is very easy. How? Because you just have to do this. You have to say 1, 0, 3 and 1. You do nothing. So initially what you did 3 of this. Suppose you subtracted like 3 of this row and you added it 1 of this row. So I'm just doing the reverse of this. So what is the reverse of this? I'm saying just change it like this. So you have this. You change 3 over here, and you whatever you added, whatever you subtract initially, you add it back. So you will get E inverse of this. So that means, so if you have this E1, so inverse is very easy. So whatever element you changed over there, you just change the sign. Okay, E inverse, E1 inverse is easy to find. So this is very easy to find. So we can also take an example to justify this. So if you take a bigger example also, suppose you have a huge example where you have a matrix 3 cross 3 and then you perform some elimination onto that. So let's say some elimination is there. Let me just find a correct example so that I will give the exact values. Give me a second or so to find an example. Okay, suppose I have this. I have 1, 0, 0, 0, 1, 0. 0, minus 4 and 1. So what is this basically telling me? It is operating on the third row, only third row, because it keep the first row similar. Take 1 of first row, 0 of second, third, 0 of third. That means first row is unchanged, second row is unchanged, but the third row was changed. How was it changed? It took the second row and then multiplied it with 4 and subtracted it from the third row. This is what was changed. So this was suppose our f. Okay, then what is the meaning of, so how can we take the f inverse? The f inverse is easy. You just have to change the sign of this. So whatever you did, you have to undo it. So you have to, the f inverse will be 1, 0 and 0, 0, 1 and 0, 0, 4 and 1. So how many of you understood this point? So here what I said is, if you have an operation of this sort, you have suppose R2 and this is operated like this, R2 minus 4 times suppose R1. This is what was operated on. So now if you have a matrix of this sort, A, B, C, D, E, F, G, H, I. So if somebody asks you operate this on this, so you can also do it in matrix multiplication way. So what you can do is, because this is saying that you have to operate on R2, so you do nothing with R2. You'll say 1, 0, 0, 0, 0, 1. It will leave the first and second row unchanged, so a third row unchanged. But you have to operate on second row. So how to operate on second row? Now it's saying take 1 of second row. So take 1 of second row. Okay, but take minus 4 times and subtract 4 of R1. Okay, and this is the operation. So if you see this over here, so this operation, this elementary transformation, if you saw this is from Gaussian elimination, and this over here is the corresponding elementary matrix. So this is called as elementary matrix, and this is the elementary operation. So that means every operation has a corresponding matrix, because anyway this is also a transformation, so this is also a transformation. So mathematically nothing changed. This is just different representations of writing it. So if I am saying R2 minus 4 times R1, so what is the inverse of this? So inverse of this is if R2 was subtracted by 4 R1. So inverse will be R2 add this 4 times R1. So you will get back whatever you started with. So that's the definition of inverse. Okay. So this also will be then having a matrix correspond to this. So in which what we have to do is we'll keep the first row as it is, third row as it is, but second row we'll have to do this 4 times 1 of 0. So that means that if this is inverse of this, so if you call suppose this as F or this as E, that means this will be E inverse. That's what I said. So elementary transformation to find the inverse of any elementary matrix is quite easy. Why? Because you just have to add that thing over here. So it was minus 4 here over here, and this was plus 4 over here. So this is what you have to remember. So any elementary transformation, if you see it over here, it can be also represented in the notation of elementary matrix. And the interesting part in that is that you have this minus 4 here, you just have to add plus 4. Okay. So what will we get out of this? Because I told you we have this A, this is E1, this is E2, and this is suppose E3. If this is a 3 cross 3 matrix, and you will get upper triangular matrix. Okay. Now what I said is, if you perform on this, if you say E3 inverse, okay, E2 inverse, E1 inverse, and you operate this on E3, E2 and E1, okay, and then you multiply with A, and what you will get is, you will also get over here, you will get E3 inverse, E2 inverse and E1 inverse, and you will get U, upper triangular matrix over here. So what you see is this whole will become I. So this A, if you see now, this will be left with just A. This A will become this into U, and if you multiply all these things, what you will get is an upper triangular matrix. You'll get a lower triangular matrix. Here you have upper triangular matrix. So from these three things, you'll get a lower triangular matrix. So this is called as LU decomposition. So do you take any of these two things now? Suppose you take E1 inverse, then you take E2 inverse. If you multiply these two things, so what you will get is, you will get zeros over here and ones in the diagonal. So you will get a matrix of this sort. So initially you are getting zeros over here, suppose, and then you will getting some non-zero entries over here. So in the lower triangular matrix, you will get ones in the diagonal and you will get zeros over here, and there will be some values over here. So this A is equal to, you broke this down, this A was broken down into L and U. So L was lower triangular matrix and U was upper triangular matrix. In the next class, we'll take a concrete example of A, and then we'll get U from it. So what we'll get, we'll also get E1, E2, probably E3 if we take 3 cross 3 example, and after that we'll find inverses of all of these and we'll multiply all of these to get L. So you'll be seeing that we'll get A is equal to LU. So you'll get this lower triangular matrix and multiply by upper triangular matrix. This factorization is very important. This factorization, whatever I told you, factorization is very important. Why? Because this won the challenge of Netflix. Just a last thing, Netflix actually launched the challenge. So they told people to come up with an algorithm by the help of which they could make their recommendation system better. So their recommendation system was to be made better. So they were giving $1 million. This was the price challenge. So what a team named Ensemble. A team ensemble came, so they did this with matrix factorization. So whatever I showed you here, but here we did what is called LU decomposition or LU factorization. They performed some other factorization, but that still was matrix factorization, and they won this $1 million challenge. Okay, the team's name was Ensemble.